All right, so this is lesson 10 for chapter 1 for IM2 called Roots and Zeros. This is the last lesson in chapter 10. So we're just going to go over some basic idea of roots, and then we're going to introduce or kind of review the idea of imaginary numbers. So I know we go over that in IM1, but it's been a while, so we're going to review that. So let's go ahead and read through a few of these pieces. Here we have fundamental theorem of algebra. Every polynomial equation with degree greater than 0 has at least one root in the set of complex numbers. So just everything has at least one solution, is what it's saying. Corollary to the fundamental theory of algebra, so it's like, the idea, the opposite idea, a polynomial equation of the form p of x equals 0 of degree n with complex coefficients has exactly n roots in the set of complex numbers, including repeated roots. So it's just kind of saying that yes, every polynomial has a root, a solution, but it might not be within the set of numbers that we're thinking that it should be in. This is going to make a little bit more sense, I think, when we go to the next page, and I can actually show you what these words mean. The Dicardi's rule of signs, if p of x is a polynomial with real coefficients whose terms are arranged in descending powers of the variable, so we should always put them in order from greatest to least as far as the powers go, the number of positive real zeros of y equals p of x is the same as the number of changes in the sign of the coefficients of the terms. So this is a way of determining how many types of roots we have. So this is, and we're not actually going to practice this one on these examples. So this is another way. We may get into this a little bit more in some further, in some future sections. But right now, we're just introducing this idea. So this is a way of counting the changes. So if I have something like this, and I'm just grabbing the problem from the next page here, or actually from the bottom of your page, like this, if I just look at the changes, so I'm actually going to ignore the numbers, and I go plus, plus. So from here to here, there's no change. But if it were different, and I had, say, instead of a positive there, I had negative, I had plus, minus, okay, there's a change here. So that's what it's talking about, the number of changes in sign of the coefficients of terms, or is less than this by an even number. So if there's one change, then we either have one root, it's the same as this number, or it can be less than this number by an even number. So if it's 1, it couldn't be less than this. It would have to be just 1. But if it were 3 times, if you had multiple pieces here, then it could be 1 root instead of 3. And this is talking about kind of real roots. So again, this is kind of mixing the two ideas where we have real and imaginary, which we haven't done for a while, so I'm going to have to remind you what that looks like on the next page here. So the number of negative real zeros of y equals p of x is the same as the number of changes in the sign of the coefficients of the terms of p of negative x. So that means we actually have to flip all of the signs. We have to apply the inverses of all of them. And then we can see the negative roots, real roots instead of the positive real roots. So it's just a way of counting roots to see how many we should have. So we know at the end of our problem if we arrived at the correct number of roots. So let's go ahead and practice a little bit of that. We're not really going to practice the rules there, the Dicardi's rules, but we're going to practice finding the roots and then stating what type they are. So with this equation we have, and I'm going to write it here just so I have a little bit more room. So we have it equaling 0, so we can factor this. Right now, the main thing I'm going to look for is, do I have any greatest common factors? So I can see x cubed, x squared, x. They don't all have a coefficient that I can factor out because this is 1. So factoring out 1 won't help me, but I can at least take 1x from all of them. So I can say x, and if I take 1x away, or I'm not taking it away, I'm dividing it away, then I have x squared plus 12x plus 32. So they all just went down by 1. So it went from 3 to 2, 2 to 1, and then this was 1. Now there's 0 or none. So equals 0. So my first factor is actually x. Now I can factor this guy. So I can even set it up. I can see it's plus, plus, which I know is going to mean plus and plus. Since it's x squared here, I know it's going to be x and x. What I need to do is figure out what my two numbers are going to be. So I'm going to take 32, and I'm going to break it down. 1 times 32, 2 times 16, 4 times 8, and that would be all of them, because the next I come to is 8. So I don't have to write 8 and 4. So remember, I want to pick the factors of 12 that add up to, the factors of 32 that add up to 12. I said that backwards, because we want them to add up to this middle term. If there was a coefficient here, I'd have to do that number times 32 and then break it down, and it would have to add up. But since 1 times 32 is still 32, I'm still following that same idea. I just don't really have to do the multiplication when there's no number in front. All right, so we want to know which ones add up to 12. So the only two that I can see would be 8 and 4. So I'm just going to fill this in, 4 and 8, and that equals 0. So now I have factored this down. So remember, once we get to this point, we say x equals 0, x plus 4 equals 0, x plus 8 equals 0. So this one's already done, x equals 0. And then I go minus 4, and x equals negative 4, because these guys cancel. I'm going to subtract 8 from both sides. The 8's cancel, and we have x equals negative 8. So here are my 3 roots. Now I was expecting 3 roots because I can see that cube there. That tells me that I'm gonna have 3 roots. Doesn't tell me what kind of roots I have. I'd have to apply that Dicardi's rule real quick to figure that out. But when I get to the end here, I can see these are real roots. So these are all real numbers. So we can say there are 3 roots and they are real. So 3 real roots, because it's asking me to state the number and the type. So I have my 3 roots. Those are my 3 answers there. And I also have to state this piece here. Okay, so let's look at the last one. And we have x cubed plus 2x equals 0. So again, I'm noticing I have an x and an x here. I can factor out at least x. And then I have x squared plus 2 equals 0. I can't factor this anymore because it's not a square and a square. It's not a minus sign. Doesn't fit in any of the patterns we know about. And since it doesn't have the 3 terms, it doesn't work for factoring any farther. So I'm just going to go ahead and say x equals 0 and x squared plus 2 equals 0. I'm going to go ahead and set them up. So this one is already done. One of my roots is going to be 0. This one, I'm going to subtract 2 from both sides. X squared comes down, the 2's cancel, and I have negative 2. This is the square root property. I can take the square root of both sides, and I'd have x squared equals, well, can I take the square root of a negative number? Doesn't make sense, because nothing I can multiply will get me negative 2. Because remember, we're multiplying the same 2 numbers to get here. So it would have to be a negative times a negative, or a positive times a positive. So this is where we have imaginary roots. Whenever we have the square root of a negative number, we have the square root, and I wrote that wrong. So it should just be x equals the square root of 2 plus or minus, because we have to do that plus or minus, and then we do I. So we take the negative 1 out, technically. This is negative 1 times 2. We're kind of separating them into 2 pieces. I have to leave the square root of 2 because that doesn't have a square root. But I comes out so that it's a positive 2 underneath. And remember, this is 2 answers here. There's a positive square root of 2i, and a negative square root of 2i. So there are 3 roots. And this time, instead of just saying 3 real roots, because that's how many there were, now there's 3 roots. There's 1 real. That's my 0. And then there's 2 imaginary. And I can see that kind of clearly because there's an I here, which is what we use to represent imaginary. So there we go. We have stated our roots, and we are all done with chapter 1. I will see you in chapter 2.